All righty, guys, there's going to be 5 times I'm going to ask you to text back a response. That's part of today's participation. Make sure when you text back a response, you send it to me only. There'll be one time I'll have you do something for fun to text to everyone, but make sure the response is me only. There'll be one time I expect you to unmute and participate in saying something. So keep that in mind. I'm going to be using the chat back to take attendance, and I'll be doing a screenshot of those backgrounds in just a moment. But first, I want to start with story time and why this particular subject is really, really important to me personally. Okay, so here's the scenario. I was raised in, I guess, a nominally Christian family in the sense it was just part of family culture. I guess we call them Christmas, Easter Christians kind of thing, for those of you who are familiar with the terminology. Faith became more real to me. And when I was about 12, 13, I read the Bible front to back in about a year. I, talked to God. It became more of a significant its importance, recognizing my need to depend on the Lord. So faith was important to me. And you're probably not shocked, but also in general, I really loved math and science when I was in high school. So keep in mind, I had these two things. Of course, faith is the primacy, but, loved God and loved math science. And to me, there was no conflict between the two whatsoever. Okay. But I want to just paint a scenario. It's about April. In my biology class, I went to a public school right down the street, Underhill High School. And at about April time, we were coming on our unit on origins, which is code for issues revolving around evolution and the like. So I want to portray what was very significant to me. So this is my science teacher, my biology teacher. His introduction. Students, we're about to come to our unit on origins and study of evolution. I don't care what you personally believe, but in the next 6 weeks, learn the material. You will have an assessment. But all the smart people believe. Now, I, as a student, I'm pausing there, and you got to realize, guys, I do not have perfect auditory memory, but I remember that phrase that my teacher said. It was like seared in my brain. It's attached to a very strong emotion, and that's why I remember it. And I didn't even complete the sentence because, honestly, as my teacher droned on for the next 5 minutes, I heard nothing of what he said, because the minute he implied that smart people believe a certain way, in contrast to people of faith, he set my faith on a collision course, because in my mind, I loved God, I loved math and science, and there was no conflict between the two. But he somehow painted a picture in which there was a conflict. And I'd like to say my faith was strong enough that it wasn't shaken or rattled, but it kind of put me on a journey, a pretty solid journey of investigating and reading books and talking and interacting with scientists about this particular faith of math, science, and faith, and origins, if you will. You can guess where I fell eventually on that debate, but it wasn't without a lot of effort. So I am not going to do to you the same thing that biology teacher did to me. I'm not going to force a contrast. I'm not going to say, you good Christian must believe, and try to put you on a pivot between, your faith and some sort of doctrinal absolute. Okay, my job is not to talk about the Bible today, but I am going to talk about math. And we're going to explore a certain type of math that is going to tease at this question. So this is the main concept we're going to talk about today. Are you and the world around you, are you here by chance or are you here by design? Because it's really what boils down to in this argument, at least in my mind, is the idea that we're either here by random chance or we're here by some sort of design in which implies a designer. And that's what we're going to explore. And we're not going to explore it from a theological or a biblical perspective or even science. This is a math class. So we're going to talk about math. What I'd like you to do is you are going to find this page in your preview notes. Okay, I think starts on page 44, if I'm not mistaken. Yes, page 44. I'll give you like 30 seconds to make sure you find it. If you don't have your preview notes, you can download the PDF from my website, Moodle. Here is the main difference between Unit 3 versus Unit 4. You're writing this down. Last lesson, we focused mostly on congruency.
Miss Way.
Yes, sir.
Is what we're doing right now the ring packet or like the preview notes?
Preview notes, sir. Preview notes, page 40.
So like the blue one?
The blue packet, yes, sir.
Okay.
Here. Blue packet.
Okay, yeah, I have that. I was just
turn to page 44, Lucas.
All right.
Yeah. So congruency is same shape, same size. And similarity is same shape, different size. Same shape, different size. Notice the symbols here. That's congruent. That's similar. Today's lesson is going to focus on the math in nature that is related to that word similar. And there's 3 statements. And after this, you're going to be saying these statements out loud. An iteration. An iteration is a repeating math pattern. So it's a pattern, it involves math, and it repeats. It's a repeating math pattern. That's an iteration. It's related to the word reiterate, which means to speak again. A fractal is a visual representation of an iteration. It's a pattern that shows self-similarity, a visual representation of an iteration. It's a pattern that shows self-similarity. Here's the main point of today's lesson. Math is always by design. Math is always by design. I need to do the light dance. Iteration is a repeating math pattern. Fractal is a visual representation of an iteration. And math is always by design. I'd like you to unmute and you're going to say these three. I have them highlighted, the red, the blue, and the green. We're going to say it, try to say it, Greek chorus style all together. Okay, guys, ready? Unmute. This is part of participation today. Unmute. We're going to do it real slow. We're going to try to get that Greek chorus style going on here. Unmute, friends. Nico, unmute. Everyone's participating. Ready? Let's say the red first. Iteration.
Iteration.
Pattern.
Flows. Okay, ready? The blue. Fractal. Visual representation of an iteration.
Pattern.
Last green one. Math
is always
by design.
Golf clap. Not bad. Math by design. You guys got that one down. All right. Next page, friends. Turn to the next page. Get ready to text back to me. What I like you to do is start counting the number of sides. Obviously, the first one's pretty obvious. Count, and that is 3 sides. I'm going to be quiet for about a minute. Okay, right now you're just writing down your answers. Yeah, wait about 20 more seconds. All righty, friends, I'm going to be calling on individuals. Get ready to unmute and talk to me. Unmute and talk to me. Abby, would you get the one on the right?
The one next to the triangle.
Yes, this one.
I got 12.
12 is correct. 12 is correct. Okay, Varshini, what about this one right here?
I got 48.
48 is correct. Nico, God bless you. You know what? I was watching some of your faces and I could tell by the way you were leaning over that you were actually physically counting these sides. And I think you're just so amazing and wonderful, but stop it. Okay. I do not expect you to do that by hand. Nico, what is the number of sides on the last one and how'd you get it? Go.
It's 192.
Yes. And what
I
did you notice?
I noticed that it was multiplying by 4, the number of sides.
Excellent. Excellent. Give me a quick thumbs up if you noticed that too. Did you notice that it was times by 4? Yes. So what you are seeing here is down below, this is an iteration. Our iteration was simply times by 4. So we started with 3. This is called an iteration table. We put in 3 times by 4. We got out 12. You input 12 times by 4, and you should have gotten out 48. You input 48 times by 4, and we got out 192. So what the number, the repeating math pattern, that's called an iteration. These visual of an iteration, these are called fractals. A visual representation of an iteration. A visual representation of an iteration. Ready? Everyone chat to me personally. Question. This last fractal, this last one right there, what does it look like to you? Give me 2 things in nature. 2 things in nature that this looks like. 2 things. 2 things. Okay. 2 things, guys. 2 things. Yep, I'm gonna wait. Thanks, Jaden. Thanks, Taylor. Thanks, Talon. Yep. Thanks, Coop. Lucas, appreciate your feedback. Aditya. Chandler, virus, that, you know what? You're totally right. I think that's the first time someone mentioned that. We certainly noticed a lot of that with the coronavirus. Snowflakes, webs, leaf. Hi, Emily. Emmeline, we are in a spider web. You are totally correct. We are on our preview notes, last page, 44. So these are some common things I've seen in the past. And the daisy, snowflake, leaf, many of you said, you know, various snowflakes. I'll add spider web to it. Absolutely. I'll add the coronavirus because yes. Okay, so once again, you all had no trouble at all instantly spotting an iteration in nature. Those are fractals. We're going to do another one. Iteration is a repeating math pattern. A fractal is a visual representation of an iteration. Here's my main point. Math is always by design. So we're going to do another iteration here. And this one, and last one was times by 4. This one we're going to divide by 2. So I'm going to start with 1. I divide by 2, we get 1/2. We're going to input 1/2. Now, those of you who freak out with fractions, 1/2 divided by 2 also looks like this. 1/2 divided by 2. Put this in the margin because I might test you this on the written test. You might have to show this, which technically is the same as 1/2 times 1/2. Remember, you can flip it by the inverse. So 1/2 divided by 2, friends, is 1/4. We put in 1/4. Again, divide by 2, which is the same as times by 1/2. We get 1/8. Put in 1/8. Divide by 2, and we get the fraction 1/16. This is an iteration. It
This
is,
way.
yes, sir.
I have to join on my iPad, on my laptop
That's-
because my iPad's about to die.
Totally get
But
that.
like, if I join on my laptop, I'm not gonna have this special background. So
I understand. Thank you for trying. I appreciate it.
okay.
So taking my screenshot here. All right, so what we just did was an iteration, which is a repeating math pattern. Now we're going to take that iteration and we're going to make it a fractal, which is a visual representation of an iteration. Just follow with me. I'm going to choose, there's literally thousands of ways we can interpret this math. I'm just going to use segments. Last time we kind of did triangles. Now I'm going to do segments. Ready? 1, follow. 1, ta-da. I'm going to color code it 1/2. So I'm going to take that 1 and I'm going to go split it into 2 pieces. I'm going to take that 1/2 and split it into 4 pieces. What you were looking at is a fractal. A fractal is a visual representation of an iteration. An iteration is a repeating math pattern, and math is always by design. So now I'm going to take each 1/4 and do it 1/8. What you're seeing is a fractal. A fractal is a visual representation of an iteration. An iteration is a repeating math pattern. And math is always by design. Okay, now don't panic. We're not going to do 1/16 on every single section. Let's just do it on one little section just so you can see an illustration. I'm going to squeeze this in here, and I'm using yellow. And 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is a fractal, a visual representation of an iteration. Iteration is a repeating math pattern, and math is always by design. Go. Remember to chat back only to me. Name 2 things in nature that this reminds you of. Remember to chat back only to me. Thanks, Lucas. Rosemary, you're going to make me. Thanks, Aditya. Thank you, Nico. Thanks, Taylor. Thanks, Coop. Thanks, Federico. Mistletoe. Someone's thinking of Christmas. Thanks, Abby. Thanks, Jordy. 2 rosemaries. Leaf, pine tree, flower, Palm tree Christmas. Yes, thank you, Isabella. Thank you, Talon. Also mistletoe, pine trees. Did everybody chat back? Everyone needs to respond, folks. I got 3 more. All right, here's some pretty common things. Rosemary is unique. I've never gotten rosemary before, but yeah, you guys had no problem noticing these fractals in real life, whether it's leaf vines. In the past, people have said lightning. Most of you said pine trees or trees. Absolutely. Other people have said frost, ferns, feathers. I think one person said feathers. Another one said mistletoe. And obviously, we're thinking about stuffing with rosemary. So keep in mind what you're connecting. An iteration is a repeating math pattern. A fractal is a visual representation of an iteration. But math is always by design. So everything you're texting back has math, and math is always by design. This is my personal favorite one. Find this page. If you have colors, colors come in handy here. This is one of our most famous iterations, very famous iteration. The first one we did was times by 4. The second one we divided by 2 or times by 1/2. This third one, we're going to say it's called sum to previous. So I start with the numbers 1 and 1, and I add, and I'm going to get 2. And then 1 and 2 add, we get 3. We add, we get 5. We add, we get 8. Five and 8, 13. 8, 13, 21. And you can keep going on there. We're going to stop at 21. You'll see why it's important that we stop at 21. So this is an iteration. The iteration is called sum to previous. Now we're going to take this iteration and translate it into a fractal. We're going to use rectangles this time. First time was triangles, right? Triangles. The second time we use segments. Third time we're going to use rectangles. So we're going to start at this box, and this box represents the 1 and the 1 rectangle. 1 by 1. Now we're going to make these rectangles slightly overlapping. So now we're going to do 1 by 2. I'm going to keep my color code going here. So watch from this corner, bounce 1 up and then go to the right 2. We're going to be working ourselves clockwise. So now draw yourself a 1 by 2 rectangle. Stay right with me. I'll pause for a second to get you caught up. Next one's green. Now we're going to go a 2 by 3. So watch what we do. We start at this corner right there, 2. That's 2, and then we're going to go down 3. So starting at this corner, right there, bunny hop, 1, 2. Now go down 3, 1, 2, 3. Close it up, make yourself a rectangle. That's the 2 by 3 rectangle. Next one's going to be 3 by 5. So down 3, and then we're going to go this way, 5. Down 3, this way, 5. So starting right here. Down 3, 1, 2, 3, left 5, 1, 2, 3, 4, 5. Close it up into a rectangle. That's our 3 by 5 rectangle. Holler at me if I'm going too fast, friends. So 3 by 5. Now we're going to go 5 by 8. So we're going to go 8, 5 to the left and 8 up. 5 to the left, 8 up. So starting right there in this corner, 5 to the left, 1, 2, 3, 8 up. 1, 2, and ourselves a rectangle, looks like so. Next one is 8 by 13. So it's like this, up 8 and to the right 13, because we're going clockwise with this. So up 8 from this corner, up 8 and to the right 13. Close it up into a rectangle. Once again, start at this corner, go up 8, which you already did, and to the right 13. Seems like a lot of work, but the end product's going to be super amazing. 13 and 21. So you have the 13 going this way, right at this corner, down 21. I won't count out loud so I don't distract you. So 13, go down 21. Okay, so we have a bunch of interlocking rectangles. All of these rectangles represent this iteration. This iteration is simply a repeating math pattern. Now, this math pattern is so famous, it actually has a name. If you think you know what the name is, text it back to me right now. If you think you know the name of this pattern, text it back to me. Don't share with everybody, just text it back to me. It has a very famous pattern. It's go ahead, just toss it out there, friends. Thanks for participating, Coop. Thank you. Lucas, thank you, Aditya. Toss it back if you have an idea. This pattern has a very particular name. Pattern. Geometric pattern. Thank you, Talon, for participating. Don't Google it. That's cheating. It is an iteration pattern. All right, friends, type the first, it is a geometric pattern, Jordy. Thank you, Federico. Yes. Okay, type the first 5 numbers just in Google search and hit enter and you'll see quickly the first 5 numbers. Type it in, hit search, text it back what you get. It's a very famous pattern. Aha. Yes. Nice job. Postal Code in Brooklyn. Seriously, Coop. This is it. Excellent. Federico, the pattern starts with the first letter of your name. So you tell us, what is it? Out loud, unmute, Joe.
So it's called the Fibonacci sequence.
Excellent. Yes. Now we're going to take these interlocking shapes and we're going to add one more thing to it. We're going to add a curve to it. So I'm going to go way in here to the 1 by 1 and the 1 by 2. Watch what I do. I'm going to do the curve in black. So I'm going to go from this corner to this corner, and you connect the corners with a curve, and then go to the next corner. I'm going to darken it with dots. So you see the beginning of a curve here. And then I'm going to go to the next corner, the 5 by 3, the 2 by 3 corner. See this dot here? Going to connect, and we kind of curve it between the corners. Now I'm going to head to the 3 by 5 corner, which is right here. Connect with a curve. Next dot there, that's the 5 by 8. Connect with a curve. The next corner is the 8 by 13. Connect with a curve. Kind of smooth it out. Last one's the 13 by 21. You artsy people probably have this curve nice and pretty. I'm going to go back and darken it all the way, starting from the beginning. Okay, kind of connect those corners. Whoops. Darken that out. This is called a Fibonacci spiral. Now keep in mind what you're looking at is an iteration. It's a repeating math pattern, and math is always by design. Here's your third chat back. Ready? Text 2 things in nature that this reminds you of. Nature, folks, nature. So you music people know it isn't a treble clef. No, is that treble clef? Nature, friends, nature. Yep. I'm seeing a bunch of stuff. Okay, about 10 more of you. Something in nature this reminds you of. Yep. Someone's hungry. Cinnamon bun. I'm seeing sunflowers, lizard tail, tree bark design, snails, she cells, fossils, shrimp. Yes, a wave. Keep it going. A conch shell. You bet. So all of you had a really easy time thinking of something in nature. And the reason why is this Fibonacci spiral is found all around you in the natural world. Conch shell, a bunch of animal examples, the curl of tails, the curl of a wave, even the wind patterns of hurricanes. Several of you mentioned plants, and even the spiral arms of our galaxy. Math is always by design. All right, we're going to come to the last 2 short videos, each of them about 6 minutes long. We'll just make it. I want you to recopy these blanks yourself. Go, I'll give you, recopy those blanks. Now I'm going to give you guys another like 30 seconds. I'd like you to skim through and just skim through these questions, pages 48, 49, and 50. Just kind of skim through them so you're familiar with them, because when we're watching the videos, I'm not going to stop for these blanks. And then the very last thing you do is you're going to write a couple sentences for each of these questions on page 51. But right now, I'm going to give you just some quiet time, pages 48, 49, and 50. Just give a quick skim through those questions. I'm going to start the videos in about 1 minute. All righty, guys, if you get right at the very end, let me just show you where on learn.vcs. If you lose track of these videos or you miss a spot, it's right here under distance learning. Okay. And then today you must submit your work. You could either print it to PDF or save it to PDF, or you can take pictures, but you must submit your work. Okay, through page 51, the entire lesson right here. And that's what I will be grading today for extra credit. Right, so starting with the first one, fractals, the hidden dimension.
Sparks, steam, smoke.
Starting with the fact that fractals and special effects. Fractals are used in all special effects.
Designers and artists the world over have embraced the visual potential of fractals. But when the Mandelbrot set was first published, mathematicians, for the most part, reacted with scorn.
In the Mathematical Intelligencer, which is a gossip sheet for professional mathematicians, there were article after article saying he wasn't a mathematician, he was a bad mathematician, it's not mathematics, fractal geometry is worthless.
The eye had been banished out of science. The eye had been excommunicated.
His colleagues, especially the really good ones, pure mathematicians that he respected, they turned against him.
Because, you get used to the world that you've created and that you live in, and mathematicians had become very used to this world of smooth curves that they could do things with.
They were clinging to the old paradigm when Mandelbrot and a few people were way out there bringing in the new paradigm. But he used to call me up.
Mandelbrot is a mathematician from the 50s, 60s, and 70s, which observed the power of fractals.
No, this is an artifact of your stupid computing machine.
I know very well that there's this line that fractals are pretty pictures, but they're pretty useless. Well, it's a pretty jingle, but it's completely ridiculous.
Mandelbrot replied to his critics with his new book, The Fractal Geometry of Nature. It was filled with examples of how his ideas could be useful to science. Mandelbrot argued that with fractals, he could precisely measure natural shapes and make calculations that could be applied to all kinds of formations, from the drainage patterns of rivers for the movements of clouds.
So this domain of growing living systems, which I, along with most other mathematicians, had always regarded as pretty well off limits for mathematics and certainly off limits for geometry, suddenly was center stage. It was Mandelbrot's book that convinced us that this wasn't just artwork. This was new science in the making. This was a completely new way of looking at the world in which we live that allowed us not just to look at it, not just to measure it, but to do mathematics and thereby understand it in a deeper way than we had before.
As someone who's been working with fractals for 20 years, I'm not going to tell you fractals are cool. I'm going to tell you fractals are useful. And that's what's important to me.
In the 1990s, a Boston radio astronomer named Nathan Cohen used fractal mathematics to make a technological breakthrough in electronic communication. Cohen had a hobby. He was a ham radio operator, but his landlord had a rule against rigging antennas on the building.
I was at an astronomy conference in Hungary, and Dr. Mandelbrot was giving a talk about the large-scale structure of the universe and reporting how using fractals is a very good way of understanding that kind of structure, which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helga von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable and my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well. And I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was frankly an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals experimentally, I came up with a very wideband antenna. And then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have self-similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas sticking out at the same time. The alternative option is you can let your cell phone look like a porcupine, but most people don't want to carry around a porcupine.
Today, fractal antennas are used in tens of millions of cell phones and other wireless communication devices all over the world.
We're going to see over the next 10 to 15 to 20 years that you're going to have to use fractals because it's the only way to get cheaper cost and smaller size for all the complex telecommunication needs we're having.
Once you realize that a shrewd engineer would use fractals in many, many contexts, you better understand why nature, which is shrewder, uses them in its ways.
They're all over in biology. They're solutions that natural selection has come up with over and over and over and over again.
One powerful example, the rhythms of the heart. Something that Boston cardiologist Ari Goldberger has been studying his entire professional life.
The notion of sort of the human body as a machine goes back through the tradition of Newton and the machine-like universe. So somehow we're machines, we're mechanisms. The heartbeat is this timekeeper. Galileo was reported to have used his pulse to time the swinging of a pendular motion. So that all fit in with the idea that the normal heartbeat is like a metronome.
But when Goldberger and his colleagues analyzed data from thousands of people, they found the old theory was wrong.
This is where I showed the heartbeat time series of a healthy subject. And as you can see, the heartbeat is not constant over time. It fluctuates, and it fluctuates a lot. For example, in this case, it fluctuates between 60 beats per minute and 120 beats per minute.
The patterns looked familiar to Goldberger, who happened to have read Benoit Mandelbrot's book.
When you actually plotted out the intervals between heartbeats, what you saw was very close to the rough edges of the mountain ranges that were in Mandelbrot's book. You blow them up, expand them, you actually see that there are more of these wrinkles upon wrinkles. The healthy heartbeat, it turned out, had this fractal architecture. People said, this isn't cardiology. We do cardiology if you want to get funded. But it turns out it is cardiology.
So his point there was that the fractal nature of the heartbeat, how it goes up and down, actually mirrors quite closely the fractal nature of mountain ranges. Mountain ranges. Here's our second video.
This way.
Yes, sir.
Is the video fill in the blanks extra credit?
Yes, it's all part of it.
Wait, this whole thing's extra credit?
Yes, sir.
Okay.
The leaves, in the branches of the trees, in the palm of your own hand. It is the patterns found in this universe. Do you see it now? I think there is a reason that our reality is constantly clouded with our own thoughts. If not for our thoughts, we wouldn't be so distracted. We would observe the present moment more, and I'm not sure if we could handle the intensity of the present moment. A single rock is filled with so many details, more than what you managed to notice so far in your life. If we actually take in all the details of the present moment, maybe we would just get lost in it. The universe seems so chaotic, so random, intricate, and complex. It is often considered to be beyond the grasp of mathematics, science, and even art. But what do you see when you look at this picture? It is called The Great Wave, a woodblock print by the 18th century Japanese artist Hokusai. Look at it carefully. A fractal is a mathematical set that exhibits a repeating pattern displayed at every scale. I know that warning alarms are ringing at this very moment when I started talking about a mathematical set. It is really easy to explain. Take a blank sheet of paper and draw a line from the center to the bottom, just like this one. Now, draw two other lines at a 45-degree angle from the top of the first line, and continue doing the same to all the lines that you draw, like this. And keep going on. And this, my friend, is called the fractal canopy, or the initial stage of it. Now put the pen down, go outside of your room, and look at the nearest tree. What do you see? A mathematical set that exhibits a repeating pattern displayed at every scale. It is not just in this tree. It is found almost everywhere in nature, in the mountain peaks, in the coastal lines, nerves inside you, the human heartbeat. It seems like the universe is following a self-similar code that repeats itself at every scale. When discussing fractal geometry, we should absolutely talk about Benoit Mandelbrot. He's a Polish-born French and American mathematician who refers to himself as a fractalist. He's the one who coined the word fractals. He said that things that are considered chaotic, rough, and complex in nature have a degree of order. He showed how visually complex things like mountains, rocks, or a forest can be created from simple rules. He even displayed it by discovering the Mandelbrot set in 1979. In his book Fractals, Form, Chances, and Dimension, and Fractal Geometry of Nature, he described how these self-similar patterns are to be seen in even the complex structures of nature. Because of his work in this area, fractal geometry is now used to produce computer-generated visual effects in movies, cancer research, telecommunication, and many other fields. One of my favorite fractal application researches is this. In 1997, a group of researchers, West, Brown, and Enquist, tried to determine whether the fractal structure of a single tree could predict how an entire forest is placed in the ecosystem. One of the researchers headed to the northwestern part of Costa Rica to a government-allocated rainforest. They measured the fractal structure of the tree by measuring the placement of the branches, the gap between them, and then proceeded to the forest to measure the placement of various trees, big and small, within the forest. They found something quite amazing, for the lack of a better word. The distribution of the branches in the tree they measured almost exactly matched the distribution of the trees in the forest. Suddenly, the work of nature, which was thought to be beyond the grasp of humans, revealed itself in the form of fractals.
If you think about it for a minute, it would be incredibly inefficient to have a set of blueprints for every single stage of increasing size. But if you have a fractal code, a code that says when to branch as you get bigger and bigger, then a very simple genetic code can produce what looks like a complicated organism.
But Mandelbrot is not the first one to notice these self-similar patterns. Remember the Japanese Great Wave? Look at the self-similar waves at the end of the giant wave in this picture. And Hokusai is not the only artist to notice this. Actually, fractal art is largely prevalent in ancient Indian architectures, and many Southeast Asian temples and monuments exhibit fractal structures. They're also prevalent in Islamic geometric patterns and African architecture. It is safe to say that almost all of the ancient cultures from around the world seem to have an understanding of this fractal geometry present in the nature. If you had watched my simulation hypothesis video, I'm including that in the card above. I've discussed whether this universe is a computer verse is most definitely a mathematician. So next time when you're outside walking or looking at a tree, give yourself a couple of minutes to really be present and register the patterns around you. Maybe the seeker of the universe is right in front of us and we're just too distracted to notice.
So just keep in mind that math is always by design. Take a moment, turn the page. I'd love your feedback on what we learned today and submit that to learn.vcs. I wish you all an amazing and wonderful, safe vacation while you're traveling. Take a moment to give thanks to the Lord for all your many blessings. Happy Thanksgiving.
So how do we submit it, like every page though?
Just take a picture, or you can, picture and learn.vcs.net.
Of every page or just this last video?
No, every page.
Oh, okay. Thank you.
What is the extra credit page?
The whole thing.
The whole thing is extra credit?
Yeah, well, your participation, the chat back, the holiday theme, the submission of the assignment, all of that is extra credit.
Okay, thank you.
10 points.
Miss Wei, when do we have to send in the picture of the email by?
I'll probably be checking him tomorrow.
Okay. All right. Thank you. You have a good Thanksgiving.
Happy Thanksgiving.